Space technology plays a major role in pushing the edge of environmental research. Satellites offer a large and broadened view of several areas of planet Earth. Therefore, a vast majority of climate researchers rely on satellite data to produce new knowledge. My name is Hiba Bidar, and in this presentation, we are going to deeply investigate the major role satellites play in enhancing our understanding of the Earth's climate system by underlining concrete and original examples of their multiple and various scientific uses. But before getting started, it is important to acknowledge that the word satellite refers to a planet or a moon orbiting a certain celestial object. However, in this presentation, we mainly mean by satellites the artificial satellites, which means the machines consisting of self-contained communication systems capable of receiving signals from Earth and retransmitting them back. With that being said, let's get started. Humankind's fascination with space led to numerous commitments to actions. From stargazing to the first space shuttle, space technology evolved greatly over the years. The idea of satellites goes back to the late 1950s, marking the beginning of the space age. Since the launch of Sputnik 1 in 1957, followed by Explorer 1 in 1958, thousands of satellites have been sent into space on missions to collect data about Earth. Today, the overall number of satellites in orbit is about 3,372 satellites. Yet, it is important to acknowledge that the world's current ability to forecast weather, monitor climate, and natural hazards depends critically on these satellite-based observations. They collect valuable, efficient, and accurate data more quickly than instruments on the ground, and thereby offer a large and broadened view of several areas of planet Earth. Satellites have certainly revolutionized how humans view the home planet. They help address fundamental scientific questions and enables a plethora of applications with important societal benefits. Continued Earth observations from space will be required to address future scientific and societal challenges. In 1966, few countries such as the United States, Canada, France, United Kingdom had a position over satellites in operation. This number increased significantly henceforth. Today, over 2,000 countries are launching and operating satellites, as shown in the graphic below. The unified use of satellites expanded across a wide spectrum, the 6 continents. For further statistical evidence, we illustrate the chart below. So please take a moment to view them. From weather forecasting to high-tech navigation systems to answering fundamental questions about the Earth's climate, satellites have become a crucial part of a wide variety of scientific endeavors and practical applications. Yet, the global positioning system plays a major role in such matters. The global positioning system, originally Navstar GPS, is a satellite-based radio navigation system owned by the United States government and operated by the United States Space Force. To sustain the Earth's environment while balancing human needs requires better decision-making with more up-to-date information. Gathering accurate and timely information has been one of the greatest challenges facing both government and private institutions. The Global Positioning System, the GPS, helps to address that need. Data collection systems provide decision makers with descriptive information and accurate positional data about items that are spread across many kilometers of terrain. By connecting position information with other types of data, it is possible to analyze many environmental problems from a new perspective. Position data collected through GPS can be imported into Geographic Information System software, a GIS, allowing spatial aspects to be analyzed with other information to create a far more complete understanding of a particular situation than might be possible through conventional means. The National Atmospheric Research Laboratory of India has been studying the application of global positioning system radio occultation data for climate change studies. The non-linear characteristics of the climate require long-term observation of temperature profile and water vapor concentrations in the atmosphere for understanding both its natural variability and its response to anthropogenically driven changes. For studies of long-term climate trends, for example, temperature, water vapor, or geopotential height at specific pressure level, sufficient accuracy, resolution, spatial, and temporal coverage of the parameter is required, since only small variations are expected over the lifetime of an instrument. The above-mentioned requirements for the studies and partly addressed by the GPS radio occultation technique, which requires no external calibration but relies on stable oscillators and is therefore most useful for climate research and weather prediction. The dataset received by the GPS radio occultation technique has been successfully used for weather forecasting. Many studies have shown that forecasting can be improved by incorporating global data from GPS radio occultation. The proof of concept GPS meteorology radio occultation experiments in the United States of America was followed by several missions, such as the Earth satellite, the SACC satellite, and the CHAMP, which stands for Challenging Mini Satellites Payload Mission Satellites. The Challenging Mini Satellites Payload project was a successful mission that collected a wealth of information by providing parameters profile with good accuracy on a long-term basis. Recently, Formosa Satellite 3 of the Constellation Observing System for Meteorology, Ionosphere and Climate, which stands for COSMIC, was launched. The constellation consists of 6 satellites with dual-frequency GPS receivers on board. The application of GPS radio occultation for weather forecasting provides data that are effectively used for climate change studies by continuous monitoring of tropopause height, which is an indicator for climate change or water vapor for all these missions. Monitoring and predicting the onset of the Indian summer monsoon is another application with a high impact on the socio-economic conditions of the entire country. Microsatellites as well have such a massive role in enhancing climate science. In the last decade, the entire space industry has been affected by budget reductions. The situation has encouraged the use of microsatellites for scientific missions as an option to develop space activities without big budgets. On 20 March 2002, after separation from the cargo ship Progress M17, a scientific and educational microsatellite called the Colibri 2000, developed by the Space Research Institute of the Russian Academy of Sciences, which has been developing microsatellites for the last 7 years, was delivered into orbit close to the orbit of the International Space Station. The spacecraft, with a mass of overall 20 kilograms, was equipped with unique scientific instruments to study lightning discharges as well as data collection and housekeeping systems. The scientific program of Colibri 2000 addressed inter alia the monitoring of tectonic activity in the ionosphere and the study of ionospheric disturbances caused by the development of magnetic storm in the terrestrial magnetosphere. A new microsatellite called Chibis, with a total mass of 40 kg, is now being developed. The Space Research Institute of the Russian Academy of Sciences has facilities for the complete cycle of ground testing of microsatellites. Some new space instruments, such as super lightweight induction magnetometers, a lightweight electric probe for measuring detention of electric fields, and a wave probe, were also developed as the Chibi's payload. These two microsatellite missions aim to study the atmosphere's layers. Today, with the new technology we possess, we know that one of the major factors of climate change is space weather. Space weather is the concept of changing environmental conditions in outer space. It is distinct from the concept of weather within a planetary atmosphere and generally deals with the interactions of ambient radiation and matter within interplanetary and occasionally interstellar space. Space weather describes the conditions in space that affect Earth and its technological systems. The Earth's space weather is a consequence of the behavior of the Sun, the nature of the Earth's magnetic fields, and our location in the solar system. It is important to acknowledge that climate change is driven by four major factors: solar radiance, greenhouse gases, volcanoes, and ENSO, which stands for El Niño Southern Oscillation. All weather on Earth, from the surface of the planet out into space, begins with the Sun. Space weather and terrestrial weather, the weather we feel at the surface, are influenced by the small changes the Sun undergoes during its solar cycle. The most important impacts the Sun has on Earth is from the brightness or irradiance of the Sun itself. The Sun produces energy in the form of photons of light. The variability of the Sun's output is wavelength dependent. Different wavelengths have higher variability than others. Most of the energy from the Sun is emitted in the visible wavelength, approximately 400 to 800 nanometers. The output from the Sun is these wavelengths is nearly constant and changes by only 1 part in a thousand, which means 0.1% over the course of the 11-year solar cycle. A variety of physical phenomena are associated with space weather, including geomagnetic storm and substorms, energization of the vanillin radiation belts, ionospheric disturbances, and scintillation, aurora, and geomagnetically induced currents at the Earth's surface. Coronal mass ejections and their associated shock waves are also important drivers of space weather, as they can compress the magnetosphere and trigger geomagnetic storms. Information on space weather is of paramount importance for humanity. One particular aspect is the study of the magnetosphere, focusing on radiation belts, in particular particles that could be dangerous for human beings. Thanks to satellites, this process is being implemented. Since 1975, each of NOAA geostationary operational environmental satellites, which stands for GOES, located in Earth's geographic equatorial plane, approximately 6.6 Earth radii from the center of Earth, have carried magnetometers to monitor the geomagnetic field and its variations. Typically, there are two GOES operational satellites: the GOES East, located over the east coast of the US, and GOES West, located over the Pacific, just west of the US mainland. At times, though data is available from more than the two prime operational satellites, the GOES magnetometer data are also important in research, being among the most widely used spacecraft data by the national and international solar and space weather research community. The data have often been used to support launch decisions for research sounding rockets. The measurements can also be used to validate large-scale space environment models of the coupled magnetosphere and ionosphere. So, as we came to the end of this presentation, I would love to point out that satellites are widely and in a wide range contributing to environmental research. They tremendously helped enhance climate science. Satellites looking toward Earth provide information about clouds, oceans, land, and ice. They are also major gauges in the atmosphere, such as water vapor, ozone, and carbon dioxide, and the amount of energy that Earth absorbs and emits. They also monitor wildfires, volcanoes, and their smoke. They generate data and help scientists predict weather and climate. This information also helps public health officials track disease and famine. It helps farmers know what crops to plant, and it helps emergency workers respond to natural disasters. Thanks to the world's renewal of its commitments and investment into Earth observing systems, satellites are nowadays playing an increasingly vital role in observing the dynamics of the Earth system and thereby guiding society in meeting the challenges posed by global changes. Today, we developed a better understanding of Earth's climate system and aim to support delivery of actions by offering sets of data to monitor the decision-making process and enable a new era of climate adaptation. That was for all. Thank you for your attention, your time, and your consideration.